Okay, so good afternoon, everybody, and thanks for a very kind introduction, Gerhard. So I'd like to start my presentation. Okay, so I'm happy to be back to Erlangen. So this is one of my most favorite places. So we have many excellent colleagues, and I like this type of the unpaved road. So I'm living in Tokyo, so I have never seen this type of road in my neighbors. And so I worked for the SX2. So it started 2015, and I worked with Gerhard. So more than 7 years. Okay. And that was a very nice opportunity for the collaboration between the DFG SPP Exa and JST Crest. And now I'm a member of the it's a strategic scientific advisory board by NHR from last year. And you can see this is a very nice memory. It's 6 years ago, and we had some coding week for the SX2 project. And, okay, so this is the agenda. And so before going to the rather scientific work, Gerhard requested me to talk about some structure of some program in Japan. Because so we have, I found several similarity and difference between the NHR program and our program in Japan, and I'll talk about those first. Okay, so this is a very brief overview of my center. It's an information technology center. So we are in charge of some information related infrastructure and something like that. And it's established 1999, and we have 4 divisions. And I'm belonging for the supercomputing part. And it's also the core institute of the some national activities. It's a JHPCN and HPCI. So I'll talk about these later in detail. Oops. So sorry, I cannot handle this. Oh, okay, okay, no, it's okay. That's fine. Okay, okay. This one? Oh. Yeah, so this is a more detailed description of the supercomputing research divisions, which I'm reading. And we are doing the services and operations of the supercomputer systems and the related research and education. So we have a long history. So the first, it's established as a supercomputing center of the University of Tokyo in 1965. So it's more than nearly 60 years. Okay. And it's the oldest academic supercomputer center in Japan, and it's a nationwide and joint use facilities. So this means users are not limited to the researchers and students of the University of Tokyo. And as I mentioned in the previous page, we joined the Information Technology Center in 1999. Okay. And we have more than 10 faculty members, including part-time ones. And so we cover the wide range of expertise from the architecture, system software, algorithm, applications, and GPU. And we have 8 technical staffs. And we have nearly 3,000 users, and 50% users are from outside of the University of Tokyo. So this is a current lineup. And actually, so this Oak Fox has just retired in the end of March. And we are operating now 2 systems. One is the Oak Ridge CX. It's a Cascade Lake cluster. And another one is also Wisteria VDX01. So I'll talk about this later in detail. And also, we have another type, cloud type systems called MDX. And it's not a supercomputer, but it's some new direction of the facility. And this is a location. And actually, so Tokyo has a lot of campuses, and the main campuses are in the center of the Tokyo. But most of our supercomputer facilities are in Kashiwa area. So it's roughly 1 hour trip by train. Okay, so I start from some programs in Japan, and try to make a very brief comparison with NHR. Okay, so users of the public supercomputers in Japan. So generally, major supercomputers are operated by national universities in Japan. And also we have some public research institutes such as RIKEN, AIST, JAMSTEC, but so majorities are universities. And it's all of them are nationwide shared systems, as I mentioned, and the users are not limited to those from each university. And main users are faculty members and researchers of the universities and colleges, and the students, and the researchers in public research institutes, such as RIKEN or AIST. And basically limited to residents in Japan by Japanese training law. But after 2008, so it has been changing a little bit. And one is the industry users. So now users from industry are allowed to access our supercomputer system. So they need a very special qualification, and also the usable amount of the resources are so limited. But so Japanese government strongly recommends industry academia collaboration. So in this direction, so we have more industry users than before. And another type of the user is a non-resident. Yeah? So basically, it's international users and foreigners. But if you have a MOU or some research project or research collaborations, we can allow so non-resident users, even from the outside of Japan, so under certain restrictions. For example, some of the users cannot browse manuals. Okay? So it's some kind of the object of the trading law, and it's I don't know that so why it's so important, but so anyway, so sometimes so they cannot see manuals. But anyway, so recently it's much more relaxed than before. And another very important aspect is so in Japan, users usually pay fee for using supercomputers. So it's corresponding to the cost for electricity. So it's not so expensive. But as you know, so if you operate the system with 1 megawatt, we need so $1 million per year. Probably it's more because of these situations, but we need to pay a lot of money. So usually we ask users to pay for this. And basically first come and first served rule. And in this case, proposal is very simple, just 2 or 3 lines. For example, so we have a Wisteria VDX1 Odyssey with a A64 effect. It's the same architecture with a Fugaku. So in that case, if you want to use the so single node, so 48 cores with 2 terabyte storage for 1 year, so you need to pay €430 per year. Okay? So it's based on the 140 Japanese yen, it's equal to €1. I'm not sure, so you feel this cheap or expensive, but so from our point of view, it's very cheap because we don't need to do anything. So everything, we just so make a program and submit the code. So the maintenance is done by the center. I think it's a very cheap. And the users purchases node hours. Okay. So for example, if you just buy the 1 node year, you can use, for example, 2,000 nodes simultaneously. But at that time, the tokens are spent very rapidly. And we have so new type of the nationwide programs using supercomputers. So they are proposed-based, and basically it's free. So users don't have to pay the fee. So recently, the weight for this kind of the program is getting larger and larger. So one is HPCI. It's mainly for the fundamental research. And another one is HPCI. So it's more so-called productive runs, large-scale computing and large-scale simulations. So each supercomputer center has its own research program, but it's a very small budget. But so recently, more than 30% of the resources are spent for such so nationwide programs and projects. Okay, so let's start with the JHPCN. So JHPCN stands for the Joint Usage Research Center for Interdisciplinary Large-Scale Information Infrastructures. So starting from 2010, so more than 10 years ago. So it's an alliance of the supercomputer centers of 8 national universities. So it's a very similar structure of the nature in Japan. So we have 7 imperial universities. They are very old universities, like University of Tokyo or Kyoto University. And one is Tokyo Tech. So totally we have 8 universities. And the core institute is the Information Technology Center of the University of Tokyo. And the total so computational amount resources is 140 petaflops. So because our big system retired, so now it's a little bit smaller than before. And so you can see from the Hokkaido, it's a north one, and this one, south one is a Kyushu University. And we have a Tokyo and Tokyo Tech. The main purpose is the promotion of the collaborative. It's a fundamental and interdisciplinary so research project using facilities and human resources in 8 centers. So basically, so the projects are collaboration between scientists and engineers and computer scientists and mathematicians in the supercomputer centers. So we have 2 categories for the project, and one is CSE, and another is the new category from this fiscal year, so focusing on the data science and data analytics. And we have another type of the category. So one is the general one, and the international one, and the industry project for both of the CSE and data science. So most of them are general projects, but we have 3 or 4 international projects. So where we can involve the international researcher. So this year, total 63 projects are adopted, and 55 CSE and 8 are data. And many of the projects are by multiple centers. So when we started this program, 2010, most of the programs are using just a single resource. But now, we can use several ones. For example, so they can select the very large scale GPU cluster and also the Fugaku type supercomputers and the Xeon cluster. So it's a very variety of the hardware. And the budget is supported by Japanese government. And so you can see, so this is a history. And so roughly this part is corresponding to 1 million euro. Okay, so you can see the budget per year is roughly 1 million euro. Okay, and so more than half of the budget is spent for the fee for the supercomputer. So it's corresponding to the electricity which I mentioned in the previous page. And 1/3 of the supercomputer fee is by 8 centers. And here, cost for the hardware are not included. So this is just for the operations. And so budget for each project is up to 2,000. I think it's 20,000. So 20,000 euro per year. Yeah, not so big. Okay. Okay, so this is my very personal point of view. So before JHPCN, we have 8 centers, but they are independent. So we are no collaborations or no conversations, and are not necessarily active in the viewpoint of the research. But after JHPCN, collaborations among centers are much more active, as well as the CSE collaborations through project. And for example, so in my case, I have collaborators in almost all centers. And so with these colleagues, we can make joint proposals for external funding. So one of these led to this SX2 project. And I think this collaboration is very nice for the promotion of the interdisciplinary sciences and also the collaboration among centers. Okay, so this provides a very brief comparison with the NHR. And last week, we have a meeting of the SAB of the NHR, and I was very impressed because you have 8 centers, and each of the 8 centers has some kind of responsibility for the certain area of the applications, fluid dynamics, molecular science, or something like that. But in our case, we have no such type of the assignment, because we started from the very independent situations, and we have no such kind of the issues. But for example, in the case of the University of Tokyo, so we have many users for the weather, climate, earthquakes, engineering, and material science. So they are the very big users. And so another feature is so we have various types of the hardware. So Hokkaido and Osaka has a cloud type systems, and the Tohoku and Kyoto has a NEC's vector systems. So now it's not a really vector systems, but they still use NEC system. And the Tokyo Tech has a very big GPU cluster called Tsubame, and Hokkaido, Tokyo, and Kyoto has a Xeon Phi cluster. And recently, some of the universities are developing the integrated or the heterogeneous systems, like our university or Nagoya and Kyushu. And so you can user can choose appropriate or favorable systems from the choices. So this is a very brief overview of the JHPCM. And actually, so SX2 is still continuing in this JHPC project. So we have 2 projects. One is the innovative multi-grid method, and it's some of the members from SX2 and also Exascale participating. So it's an international project. And so in the case of the international project, reading PI must be resident, so Japanese guy. So actually, so I was a reading PI at the first time. But now so it switched to my younger colleagues. And at least one of the co-PIs must be non-resident. So currently, one of the co-PI is Matthias Bolten from Wuppertal. And it's a collaboration among the Hokkaido, Tokyo, Nagoya, and Kyushu. And another one is high performance, adaptive precision, high reliability computing. So we have many SX2 members here. So this is not the international project, actually. Okay, so next one is HPCI. And HPCI stands for the high performance computing infrastructures. And the structure is, so we have a top national flagship systems. In the German case, we have 2 or 3 such systems. But in Japanese case, it's only one. It was K, now it's Kugaku. So basically, they are the weekend system. And so most of the supercomputers in this HPCI are called a second tier. Okay? And so second tier includes the JHPCN centers, which I mentioned before, and University of Tsukuba. So University of Tsukuba is a little bit special university, and it's separated from JHPCN. And NII, JAMSTEC, and AIST. So they are public research institutes. And another feature is we have a large-scale shared storage. So we have 2 systems, both in Kashiwa, in our campus, and Kobe in Riken. So both has more than 50 petabyte storage. And this program is focusing on large-scale simulations for not fundamental research. And the budget for each project is up to 10 times of the JHPC project. It's much larger. Okay, so this is the structure of the HPCI. And we have 2 big storage. Yes, so yeah, this is a history of the supercomputer centers in the University of Tokyo. And now we are in the beginning of the fiscal year of the 2022. And this system, Oakless Fax by Fujitsu, The peak performance was at 25.0 petaflops, just retired. Okay, so I show you some ratio of the assigned resources. So general case and the industry case, and so they need to pay some fees. And this green part is a project, so they don't need such as a HPCI or HPCI. And these old systems, T2K or OpenFX or OpenFX, so you can see, so most of the usage are by this red part, so they pay. And this one is a compatible system with a K computer, and so we have a little bit larger amount of this kind of project users, but it's less than 20%. Okay, so I'll show you another type of alliance. It's a JC-HPC. Okay. Yeah, sometimes I so I say this JHPC or something like that. So it's confusing. Okay. It's a joint center for advanced high performance computing. It's from 2013. It's a collaboration between University of Tsukuba and University of Tokyo. So in this case, we combine the budget of the two centers to introduce the big systems. So this is a very rare case, and it's the first example in Japan, and probably it's very difficult type of activity all over the world. Those are two independent national universities, and so combine such budget. So the purpose of the JCHPC is the promotion of the computational science and design and procurement and operation of the large-scale systems together. So our first system is an OpenSpace. It's called OFP, and it's a very big Xeon 5 systems. And at the first appearance to the top 500 in 2016 November, it was at number 6 in the world and the number 1 in Japan. So it's faster than K computer. So it retired in the end of this March, and so final ranking was 39th. So it's very high. And actually, between K and Fukaku, so it's worked as a national flagship system in Japan. Okay, so this is one of the the activities of the SX2 project. So unfortunately, so this is not the award winner, but the finalist of the Hans Moyer Award. It's a best paper in the ISC HPC. So here we use the OFP for SPACs and PITS thing, and we compare the two systems for some quantum simulations. Okay, so this one is another system. It's a read-bush. It's a GPU cluster, and we still have a large amount of red part. But in the case of this OpenSpace Xeon 5 cluster, you can see we have more green users, and we have more such users by projects. And you can see 2019 and 2020, so we have a very large numbers, more than 60%. So in this time, K was shut down and Fugaku didn't start working. So yeah, during these times, so this system was some kind of a national flagship system. So you can easily see that situation from this data. Okay, so this is the new system. Okay, so I spent almost 30 minutes for this part. Okay, so next I'll talk about our systems and our activities. So as I mentioned, we are operating in two systems, and today we are focusing on these new systems. Just 1 year old, Wisteria B01. And so, as I mentioned, so this is the history of our supercomputer centers. So basically, each system has a 6-year lifetime. And we have a budget to operate 2 systems. And so ideally, every 3 years, we can get a new systems. You can see in the beginning of this century, we can keep this cycle. But so after that, so we have some blank here. Okay? And for example, in the case of the off-press packs, the schedule of the development of the Intel G05 was delayed. I think it was 2 years later than expected. So, and in order to fill the gap, we are introducing the small system. So finally, we have 4 or 5 systems now. But now it's only 2. Okay? This one and this one. And recently, we have many systems with GPUs. Okay, so this is the research area based on the CPU hours, and this is the multi-core clusters in fiscal year 2020. And you can see we have many usage for the engineering or earth science and material science or energy and physics. So this type of the computational science is a majority of the users traditionally. But if you see the workload for the GPU cluster, so this is read-bush H and read-bush L, so you can see the color is very different. Okay? So we have a large amount of users from the information science related to AI or bioinformatics. Okay? And we have many users for the genome science and also medical image recognition using the machine learning. So we have a lot of such new users in the GPU cluster. So we have a very different type of users. And as I mentioned, traditionally, we have a lot of users for the earth science. So this is a climate and weather, and this is a solid earth, like the earthquake simulations. And this one is very interesting. It's a geologic CO2 storage for reducing the global warming gas. And so this one is a very interesting. It's a real-time prediction of the severe rainstorm by off-press packs. And so in that case, we utilize observational data from the very big radar system in Tokyo area. And so we estimate the thunderstorm 30 minutes ahead or something. So originally, it was planned to do the real-time thunderstorm simulation during the time of the Tokyo 2020 Olympics. But so unfortunately, it was not held. And the next year, the Olympics was done. But at that time, they used Fugaku. But it's a very nice computation. And also, our systems are used for the COVID-19 simulations. And so 2020, we have 14 projects by HPCI, and 6 of these accepted projects use a universal Tokyo system. So I believe some of you have seen this droplet diffusion simulations. It's my colleague, Professor Tsubokura from Riken and Kobe University. And he mainly used Fugaku, but at that time, Fugaku was very crowded. And he also used our system. Okay, so this is a usage ratio. It's a little bit old statistics. And generally speaking, so this our system are very busy. And recently, we have a new storage called Ipomoea. So Ipomoea is a Latin name of this sweet potato. So traditionally, each supercomputer has its own file systems. So they are independent. But as you know, number and size of the files are increasing, and it's inconvenient for the users. So this time, we have a shutdown of the off-press packs with a 25 petabyte storage. So it's a very huge amount of the storage. And in order to avoid this inconvenience, so we decided to introduce a common shared storage. So this is not so fast, but it's big and it's available from various systems in our centers, and including the future systems. And the operation period is 5 to 6 years, and the size is like this. And we try to prepare the 2 file systems. And one of these is replaced every 3 years. So that user can so keep the files without new copies. And the Ipomoya one, so we just started the operation, and it's public use from the June 2022. Okay, so next part is a rather scientific activity and our new systems. So as I mentioned, so we have various types of the workloads, CSE, big data analytics, and AI machine learning. And so CSE is so very popular in the CPU cluster, and the GPU cluster, we have a pink and a light blue, like this part is increasing. And the integration and convergence of the simulation plus data and learning, we call this S+D+L. So this is very important towards Society 5.0. Society 5.0 is something like Industry 4.0 in Europe. And so it's a super smart and human-centered society by digital innovation, such as IoT, big data, AI, etc., and by integration of cyberspace and physical space. And so it's a bunch of buzzwords. But so you can imagine so what is expected. Okay, so considering these situations, we had some project called BDEC. BDEC stands for the Big Data and Extreme Computing. And it's a platform for integration of the simulation, data, and learning. But in our case, we are focusing on this simulation part. And the data and learning are supporting the simulations. So it's called AI for HPC or AI for science or some kind of digital things. And this plan started in 2015, so 7 years ago. And the Wisteria BDEC, which started operation last year, May, this is the first BDEC system. Okay? And this is the platform for integration of S+D+L. The peak performance is 33 petaflops, and the aggregate memory bandwidth is 8.4 petabytes. So it's by Fujitsu. So this is a 4.5, so mega VA. So you can imagine so how much so do we have to pay. Actually, so this is a upper limit and usual operation. So power is not so big as this. So we have 2 kinds of nodes. Okay? So it's a very heterogeneous system. So one is a simulation nodes called Odyssey. So it's based on the Fujitsu's primary HPC FX1000 by A64FX. So it's the same architecture with Fugaku. And so almost 80% of the total system is so in this Odyssey part. So roughly, so this is the 120 of the Fugaku. So another part is called data and learning nodes, Aquarius, and it's focusing on the data analytics and AI machine learning. So it consists of the Intel Xeon Ice Ray and NVIDIA A100 GPUs. And totally, we have 360 GPU cards, okay? And the peak performance is 7.2 petaflops. And some of the this data and learning nodes are connected to the external resources directly. Thus, we can easily introduce external data with the external resources. And we have a shared file system and a fast file system. So this is the most recent ranking. And actually, so far, not so far, until the end of May this year. So these 2 parts are so operated separately. But now the software is ready, and from this June, so you can use these two systems simultaneously in certain purpose. But so yeah, you can see now the Odyssey is the 20th in the world, and Aquarius is the 115. Okay, so this is a research area. So last fiscal year, and, you can see GPU cluster, more pink. But this is the Odyssey, and this is the Aquarius. And we have a lot of the Earth and space science users and engineering users. And also, many users from CSE are also using Aquarius. It's a GPU cluster. So we expected the color is like this GPU cluster, but you can see many computational science users. So it's very nicely balanced. Yeah, so this is how we utilize our systems. So we have simulation nodes here, and so these are the data running nodes. So we are run the simulation codes, and so generally scientific simulations are non-linear, and we need to do a lot of parameter studies. And in order to optimize the models and the parameters, we utilize the external data and also data assimilation and machine learning. And we apply this type of cycle, and we can reduce the time for the parameter studies dramatically. So that is our purpose. So this is the hardware, and so we are developing the software to support this. So it's a 5-year project supported to Japanese government since 2019. So the PI is myself, and budget is not so big, but so we are developing this type of software called H3 Open BTEC. So this is members, and we have many overlaps with previous SX2 project from the Japanese part. And we are also have the international collaborators, and Gerhard is one of the key persons for the international collaborators. Okay, so we have 3 innovations, and the first part is new principles for numerical analysis by adaptive precision, automatic tuning, and accuracy verification. So I believe so many of you you are familiar with low precision or mixed precision computing recently, and we try to utilize such low precision to get more efficient computations. So second part is the integration of the machine learning and simulation. It's called data driven approach. And the third one is the software and utilities for heterogeneous environment, such as Wisteria 01. So I just briefly, so this is a very small figures, small letters, and so you can read later. So this part is the adaptive precision computing with FE42 and FE21. And in A64FX FUGAC type architectures, so they support FE16. So you can easily use FE16 half precision from the compiler. Okay. But so they are very small digit and not so stable. And so we are developing the some intermediate precision, so between FP32 and FP16. So this is FP21, and the FP42 is between the FP64 and FP32. And so yeah, so far we can get a very nice and so in the certain part we have very stable computation. I skip the detail here. So next one is the prediction of the CFD simulation by deep learning. So this is also done by my colleague, Professor Shimokabe. And this is a transient 2D CFD simulations using a lattice-Boltzmann method. So our motivation is trying to predict that 10 steps ahead by machine learning. Okay? So that we can save the computation time. And so in this case, it's successful, but so yeah, it's not so easy for the 3D or more complicated case. But yeah, it's possible so by doing this. Okay, the third part is a software for the very heterogeneous environment. And as you know, so Wisteria Extra is the first really heterogeneous system in the world. So we have, for example, many computer centers as both of the GPU cluster and multi-core CPU cluster. But there are no examples so combining these heterogeneous systems. So I believe this is the first example for this type of computation. Okay, so actually, so these two parts are connected through InfiniBand EDR with 2 terabytes second. So it's a very rich network. But so we have a very different architectures. For example, we cannot run that so single MPI code over the Odyssey and Aquarius. And so we develop a very special software to utilize a very primitive software for the InfiniBand. And we can do the programming very similar to the MPI interface. So we are developing two software. One is a H3 OpenSys weight IO socket. So it's a communication library between these. And another one is a multi-physics coupler to operate the two types of the programs. So this is the API of the weight IO socket. And so instead of MPI, it starts from the weight IO. And we are now supporting the very MPI-like functions. And the interface is very similar to MPI. And that's inside each groups, we use MPI, and outside, so you can use this weight IO. And another part is the coupler. And so coupler is usually the weak coupling of the multiple applications, such as fluid and structure, and ocean, and atmosphere. And but our coupler is a little bit different, and we try to combine the simulation workload and machine learning workload, so using coupler. So that's our new feature of the coupler. It's called H3 Open Util MP, or MP stands for the multi-physics. And as I mentioned, so we can do the simulations on the Odyssey, and we do the machine learning workload on Aquarius. And we communicate with this InfiniBand EDR through weight IO library. So these software stacks just completed in the end of this May. And from this June, so users can use this software. So this is last year, and this year we can utilize the system. So one of the examples for such kind of the systems and software is a 3D aspect simulation with real-time data observation and simulations. And so in Japan, as you know, we have a lot of aspects, and so yeah, it's a very critical issue. So usually, in the case of the wave propagation of the earthquake simulation, we assume some source term here, and we do the so-called forward simulation. It's like this way. But so it's very difficult to define this kind of source terms, and instead of that, so we utilize observational data. So because we have more than 2,000 such points for the observations, and it can be obtained by a very nice network called JDXNet. And we can obtain such kind of data in real-time manner. And so by interpolating these data, we can easily generate the initial conditions. So this is our method. But so this means so we need the observational data, and so we cannot predict the future result. And the first part we do the combination of the assimilation and simulation, and at certain time we need to switch to the pure simulation. So actually, so this simulation is very simple. It's a very simple 3D finite difference method. And so if you apply the order of the thousands of nodes, we can solve the problem 10 times faster than the real problem. So yeah, we can utilize this. Okay, so this is one of the results. It's about the 2007 Niigata earthquakes. So this is Niigata, and this is Tokyo, and we have roughly 250 kilometers away. And, so it needs more than 100 seconds to reach here. And if we have a very distance, we can easily predict the earthquake. But if the so center is very close to the Tokyo, it's very difficult. But if we apply this type of the method, we can get a more accurate solution. And so last year, we developed the system to this our new computers. And now the observational data of the past earthquakes are on the external servers. And so we can get this data to this Aquarius and apply the filtering. And after that, we do the data assimilation and computation on this Odyssey. Then visualization is done by this Aquarius. And we have already developed these systems, and so we can use this. And so in this case, we use this weight IO socket, which I mentioned in the previous part. So this kind of the simulation is very nice for the emergency information for the safer evacuation. But this kind of events are not so frequent. And so we try to utilize this type of system for the improvement of the 3D underground model. So actually, 3D underground model is very uncertain. And every time we have a small earthquakes, we apply the inversion analysis, and that so improves the 3D underground structure. So we try to utilize the small earthquakes, and so combining with the machine learning, we try to construct a more sophisticated 3D underground model. So I skip this part. Okay, so now our system, MATLAB, is also available. So personally, I don't like MATLAB because so people who like MATLAB don't do programming. Okay? But so recently, I changed the mind because MATLAB has a very nice capability for the machine learning and data analytics. And so yeah, from my point of view, so we can utilize such kind of capabilities. And we try to combine this capability to do some integration of the simulation data and learning. Okay, so I'll quickly talk about the future perspective. Okay, so one is Faisal passed defense yesterday. And he developed the craft library. So it's a checkpoint based fault tolerant library. So it's very nice. So we are long collaborator, and several years ago, so 4 years ago, so my student stayed here 1 week and worked with Faisal. And so my student developed this PFM craft. So this one is a parallel finite element code. And we start from the, so for example, 8 processes. And the two processes are down. And so instead of adding the spare nodes, we just use as a 6 node. But so you see, so it's a load imbalance. So we try to apply the load balancing here, and we continue the computation using the small number of nodes. So that's the master thesis. But recently, I'm trying to use this idea for resource management or provisioning of the supercomputer systems under urgent situations. So we are running the 3 types of jobs here. And we have some urgent jobs with a higher priority. So in that case, we can shut down all 3 cases or postpone or resume. But instead of doing that, we reduce the resources for these systems application. Then after finishing this urgent jobs, we can recover the original setting. So that we can utilize the supercomputer system in more flexible manner. But actually, so it's not so easy. So each application must be equipped with this type of the library. But so for example, if the users with this capability during this time, they don't have to pay any node hours. So it's a good motivation. So actually, fault tolerance is basically based on the fault tolerance, but we can utilize such technology for this type of parts. So I'm thinking about that. So next generation or next generation, we try to utilize this type of that. Okay, so we are now shifting to the GPU and accelerators in next 10 years. Because so if you want to get the maximum performance under constraint of the power consumption, I think the GPUs or accelerators are only choice. And we are now introducing 2 systems. One is very small, called Wisteria Mercury. It's introducing next year. And another one is OFP2, starting in April 2024. It's a successor of the OFP-Spark. It's a collaboration with the University. So this one is only 100 GPUs, and this one is 100 petaflop system. But basically, we are trying to introduce same GPUs like this. So actually, so we have more than 3,000 users for the OFP-Spark. So they are familiar with the multi-core system. And it's very difficult to perfectly switch to the GPU cluster. And we need a certain amount of time and human resources for that. And University of Tokyo considered this for the Wisteria VDEC01, but finally gave up this idea at the fall of 2019. And the current situation is we have various GPUs and programming environment, and also good for the new user of the GPUs. Okay, so 10 years ago, we have only CUDA. But after that, we have OpenACC. But now it's much easier. So we have standard language or OpenMP offloading. OpenMP offloading is not so easy, but anyway, so I think it's time for switching to GPU. Okay, so this is a Wisteria Mercury. And it's a small system supporting this Aquarius. And this is a prototype of the OFP2. And OFP2 is, so as I mentioned, target peak performance is 100 petaflops. And it's a very big one. And we should start supporting as soon as possible. So hopefully before this year fall. Okay. And so yeah, we need to define the architecture of the GPU as soon as possible. So we are now asking that some benchmarks, but I skipped the detail of this part. So anyway, so we will soon decide the architecture of the GPU and start the porting as soon as possible. Okay, so next one is this BDEC02. So it will be introduced 5 years from now. Okay. So this is also the platform of the digital twin S+D+L. And we are thinking about introducing DPU, IPU, quantum-inspired devices, etc., for supporting the workload for the data and learning, such as Graph Core, Sambanova, Cerebrus, Puma, or Digital Annealer by Fujitsu. And some of them can be also used for HPC simulations with a certain constraints. And we have been using Fujitsu Digital Annealer since 2019, so mainly focusing on the combinatorial optimization. So the big issue is a programming environment. So in order to combine such kind of very special devices and the general supercomputers. And but actually, so there are some examples of the prototype in the DOE labs. And so I expect this will be done 5 years from now, but so it might be earlier than this. And so, yeah, one thing I'm expecting this is so trying to combine this type of devices with usual supercomputers. Okay. Yes, thank you very much for your attention. Sorry, it's 1 hour.
Okay, so thanks a lot to Kengo for his very interesting and broad talk, and especially the last perspectives on your strongly heterogeneous system. BDEC2 is very interesting. And so this is also your Aquarius and Odyssey system is very heterogeneous. So are there any questions from the audience? Aisha has a question. Aisha, maybe you come to a microphone here so everybody can hear.
Maybe now it's visible. Are you? Okay, so from you actually. So you presented in your talk around and that you have this open source library, which is replica for the NPI. So this H3 open weight IO socket. So did you, first of all, is it open source? And second is that, did you have a detailed comparison with MPI library? Like you have your routines of weight IO, I send, I receive, and how in that did you perform your analysis in comparison with MPI?
Okay. So basically, it's just developed, and we're still doing the evaluation. But so yeah, we plan to do the open source.
It's open source.
Yes, yes. And as for the performance, it's not so good.
Okay.
And mainly because of the latency. So because we are running the 2 different systems. And we have InfiniBand between these. And so we have 2 latencies from Aquarius and Odyssey. And currently, this overhead by latency is not so small. So that's a big problem.
Okay, so this project is still going on? Or?
Yes, yes. So we are trying to so improve that. And so now we just do the computation. So it's a very first stage, and we try to improve the performance.
Okay.